Hello everyone, my name is Kak Hoàng Ngo. I'm now working in Chalmers University of Technology in Sweden, and it's my great honor to receive the Impact Science Second Prize from Sonta Foundation for my PhD thesis, Non-coherent wireless communications, fundamental limits, and system design. I would like to express my gratitude to Sonta Foundation and also to my supervisors, Professor Sheng Yang from Sonta and Dr. Maxime Guillou from Huawei Technologies France. Now I'm going to give a very short presentation of my thesis. My thesis is in the area of wireless communications. The fundamental problem of communication is that of reproducing at one point, either exactly or approximately a message selected at another point. In a wireless communication system, we typically have a source transmitting a signal over a channel to a destination. In the source, a message is first selected and then encoded into a sequence of bits and then mapped into a sequence of symbols to be transmitted. In the destination, based on the received signal, it first detects the transmitted symbols and then decodes the bits and decodes the message. The main challenge here is that the received signal is not the same as the transmitted signal. There are both multiplicative noise and additive noise in the channel so that the channel output can be written as the product of the channel matrix H and the transmitted signal added with the noise. This additive noise is typically assumed to be IID Gaussian, so it is independent and unknown in each channel use. On the other hand, the channel matrix is also random but remains constant during a certain amount of channel uses, T, which we call the coherence time. Now, if T is long, then we can assume that we can estimate H with negligible cost. However, in many applications, T can be very short. Think about the situation where the transmitter and receivers are moving very fast, like in vehicular communication, or where the packet is very short, like in machine-to-machine communication. Then in this case, it is more practical to take a step back and assume that the channel matrix is unknown a priori. In this case, we have non-coherent communication. There are some main problems in communications. First, in terms of the fundamental limits, we want to know how much information we can transmit and then receive reliably over the channel. Here, reliably means that if we encode a message over a large number of channel uses, then we can decode it with vanishing error probability. The second aspect is system design, and here we list only two questions. In the source, we want to know how to map the bits into the symbols. In the destination, we want to detect the transmitted symbols and then demap them into bits in an efficient and effective way. In this thesis, we address these questions for non-coherent wireless communications. First, in terms of the fundamental limits, let's consider a system with one transmitter with M antennas and a receiver with N antennas. The channel output is given in this way as you have seen, and the channel input is subject to a power constraint P. The question is again, how much information can we communicate reliably? And the answer is given by the channel capacity, obtained from a maximization of the mutual information between the channel input and the channel output. The channel capacity is unknown in general, and only some approximations are known when P is large, so we can ask a relaxed question. How many extra bits can we communicate reliably every time we double the power? This number is called the degrees of freedom and given by the limit of the ratio between the channel capacity and log of the power when the power goes to infinity. If the channel matrix has IID Gaussian entries, then it's known that the degrees of freedom is given by this formula, where m star is the minimum between the number of transmit and receive antennas and 1/2 of the coherence time. Here, m star is the optimal degrees of freedom you can achieve if you know perfectly the channel, and 1 minus m star over t is a penalty due to the lack of the channel knowledge. Our contribution here is a proof that this number d is also the degrees of freedom for a more general setting where the channel matrix has a finite entropy and finite second moment. We also have some further contributions for the multiple access channel with multiple transmitters and one receiver. We found the optimal degrees of freedom region for the two-user case where each user has a single transmit antenna. For the broadcast channel with one transmitter and multiple receivers, we derive some achievable rate and degrees of freedom regions for the channel with a spatial correlation, that is when the transmit antennas are not independent but correlated. We now turn into the system design. In the source, we want to map the bits into the symbols to be transmitted. We first divide the bit sequence into equal size groups, and we assign to each group a vector or matrix symbol. The set of all such vectors or matrices is called the constellation, and a good constellation design for the non-coherent channel is known to be geometry-based. So we can construct the constellation as the backing or a set of points in the manifold of subspaces. In the case of single transmit antenna, the symbols are simply unit norm vectors, which can be represented by points on a hypersphere. Our contributions here is the design of a practical constellation called Q-split for the SIMO case, where the transmitter has a single transmit antenna. We also propose some constellation design criteria and constructions for the multiple access channel. Next, for the destination, we want to detect the transmitted symbols and map them into bits. And our contributions here is a simple rule for detection and mapping for Q-split constellation that exploits the structure of the constellation. For the multiple access channel, we also propose a multi-user soft detection scheme based on expectation propagation, which is a message passing algorithm on graph. Finally, let me conclude the talk with this diagram. The focus of my thesis is on non-coherent wireless communications in which we don't know the channel matrix in advance, and it is irrelevant in practical scenarios. In the thesis, we have addressed some questions in terms of both the fundamental limits and the system design for non-coherent communications. Thank you for your attention.